Okay, good morning, everybody. It's 11:10. It's a brisk day in Toronto. I've got my winter coat on now when I ride my bike, and I'm thinking about breaking out my ski helmet instead of my bike helmet because my ears were getting pretty cold. So I've got the screen shared already. Today's topics are, we're going to be using this work energy principle, this idea that the initial energy plus the work done in the system equals the final energy, and we can use that to solve problems. There's a team up quiz that's going to happen today, and then we're going to get into inelastic and elastic collisions, and we're going to solve a problem on that. And when you get into elastic collisions, one of the examples of this is that the outer layers of a supernova, as it's collapsing, can actually elastically collide with the neutron star core and then get bounced way out into space with a huge amount of energy, and actually seed the whole galactic medium with heavy elements. But first, before we get too far here, I want to do this demo behind me before, oh dear. I was going to say before my screen goes orange, but I think it's already too late. I don't know if we can do this. That's getting really cold. So what I wanted to do was talk about internal energy. So dissipative forces transform macroscopic energy, meaning like things that are actually moving, into internal thermal energy, which is little random motions of the particles inside an object. So internal energy is the microscopic energy due to random vibrational and rotational motion of atoms and molecules. And if you've got kinetic friction, you can solve for the change in internal energy as being the friction force times the distance. And here's this. Here's this energy conservation equation. But now we have another energy term which comes in the final energy, which is this delta U internal. So there's kinetic, and delta U internal is the increase in the internal energy of the system. There might be some other potential there as well. If the internal energy is increasing due to kinetic friction, which acts opposite to the displacement, then there's this equation. The delta U internal is Fk times d, and we'll do some examples of that. But let me stop my screen share for a second. Keep that. And see if we got any ability to do this. Yeah, it's gone totally orange again. This camera, once Pi has set it up, seems to have about 5 minutes before it goes totally orange. Idea being that this is, anything that's hot will radiate in the infrared, and this is an infrared camera. So if we've got surface and we warm it up, yeah, I don't think it's. Pi, do you want to come in? There's an old saying, which is that lecture demonstrations in biology always smell bad, and lecture demonstrations in chemistry always explode, and lecture demonstrations in physics never work. So. It went orange.
Yep. Yeah. Just keep it up.
It was working fine just before the call started. Is that the effect of it? Let's bring this in. I guess that's the. I think you need a new phone. Okay. Yeah, we had it working before, but I guess we should just record it, right?
Yeah.
Just do a YouTube of it. This is not working in real time.
Yep.
Okay, but thank you anyways. We'll do a recording of it. All righty, everybody. All right, we're going to turn this off. You guys. Okay. Let me do, back to my share screen. Sometimes YouTube is better than synchronous. All right, we're going to do the face thing. This is a bit ridiculous, but give you a chance to decide on that. I have to get my screen together anyways. Okay. Look at the chat. Yeah, there was someone else in the call for a little while. They turned off their video. Okay. All right, let's see what the vote is. Anybody else want to chip in here if you care? Ding, ding, ding. 3, 2, 1. Share results. So 169 of you voted for flowers and hair. Okay, that's fine with me. Let's do video filter. Okay, good. So the other thing that's going to happen here, I said there was something about Movember preview. So I did shave this morning, but I'm going to try to grow a mustache for the month of November. Okay, last night, you should have all received an email at your mail.utoronto.ca account from the CrowdMark mailer that there's a new assignment waiting for you. You have to open this email. You have to click on Go to Assignment, which will take you to a uToronto login page, that same one that you log in to get on Quarkus. And then it'll go to CrowdMark, where you should see the Chapter 7 pre-quiz. It's 2 questions in a very similar format to Midterm Assessment 4, which will be on November 17th. Oh, look, it's working again. Look at that. Okay, so the surface heated up. Wow, that's just bizarre. You can also convince yourself that this works if you just rub your hands together, then they heat up as well. Okay, so that's good. It all worked out. Okay, so just like for midterm 2, you need to write your answers on the answer template sheet with the 4 steps, and then upload an image, either a PDF scan or a JPEG image or something of your work. This assignment, the Chapter 7 pre-quiz, you have 5 days to do it. A very similar assignment to this, in the exact same format, will be emailed to you on Tuesday, November the 17th at 8:10 p.m. And you will only have 35 minutes to return it up to the CrowdMark. So you have to do it in the half an hour and then upload it. It's all synchronous. And there'll be another one, midterm, the alternate sitting will have another CrowdMark assignment that will be assigned to some of you, which will be the same day, November 17th, but at 10:10 p.m. Okay. This Chapter 7 pre-quiz is a practice run. I'm not hiring the markers for it, but I'm going to go in and try to mark it myself and just give 16 homework credits for your completion and getting, so I can see the images and all that stuff. If I can't see the images, and then you'll get a 0. If I can see the images, you know, and they look like you've done some work, then you'll get 16. So let me open up for questions here. The Chapter 7 pre-quiz will not be carefully marked. You get an next midterm in an email and not on Quarkus, that's correct. Although I think I can also post a link on Quarkus to it. Shu Hai, did you have a question?
Sorry, I accidentally clicked on that. And I didn't notice.
That's okay. What about Ava?
Hi. I was wondering if the practice one is also 35 minutes long?
No, the practice one you should have now, but it's not due until Tuesday, so it's 5 days long.
Okay, so it's not like limited when we open it.
No, yeah, the
time.
CrowdMark doesn't have a timer thing like the quizzes, like the multiple choice quizzes. That's a great question. Multiple choice quizzes have this timer function in addition to the window, but these CrowdMark things, they just have a window. So it's going to be a 35-minute window on November 17th, but right now it's a 5-day one.
Oh, okay, I see. And can we do it on our tablet, or do we have to do it on paper and take a picture?
Yeah, tablet is fine as long as I end up with the PDF at the end that I can read.
Okay, thank you.
Yeah, sure. Awesome. Good questions. Ishman?
Hello, Professor. Can you hear me?
Yeah, I do. Yeah.
So about the pre-quiz 7, till what date do we have, the due or the deadline to submit this pre-quiz? Like, is it on the modules of Quarkus, or it's just in the email on the announcements?
I think you just see it on the email, right? Hopefully you've gotten
Yeah.
it, and it's due on November 3rd, Tuesday.
Okay. Thank you, Professor.
Yeah, you're welcome. And Jenny?
Hi, sir. So in the email that you sent us,
Yes.
it says that a very similar assignment will be emailed to you on the Tuesday, November 3rd at
Yeah,
8.
that's a typo. I'm so sorry.
Okay, yeah.
I have
Okay.
updated the announcement. It should have said November 17th.
Okay, yeah. Okay. Yeah.
Sorry about
thank-
that. Hao Tian?
So like last midterm, because I tried to convert my picture to JPEG, and it kind of didn't work, and the image is really blurry, and like the TA couldn't mark it. So like it's because I'm using iPhone, so like the picture are a different format. Is it okay to upload the HEI something format instead of?
Yeah, I don't think the HEIC is going to work. You have to go onto your iPhone and turn off this high efficiency mode. I was able to find it in the settings for my camera, and I put it in. I can send another announcement, same sort of thing I did last time, which is you go onto camera and you go to, where is it here? I put it in that announcement last time. You find the settings for your camera, and you go to something to do with the storage mode. Okay. I guess I can let you guys chat about that for a bit. If you have a good smart thing to say in the chat window about HEIC, that would be helpful. Okay, let me do an example. A small box of a mass equals of 10 kilograms. So let's write this down. So here's your knowns. M is equal to 10 kg. Is released from rest at an initial height of HI equals 2 meters. Okay, on a frictionless incline as shown. At the bottom of the ramp, it encounters a friction full surface, a friction rough surface with a length D. I'm going to call this D maybe friction or something, is equal to 1 meter, and mu sub K is equal to 0.25, something. And then a frictionless circular rise up to H final need, H final, it's question mark. Okay. And what I'm going to do is define the system is the box plus the earth, because MGH is going to be important, plus the surface, all the surfaces involved. And so what's going to happen is delta U internal equals F sub K times D will be generated in the flat slide. Okay, as it slides across that rough part, it'll generate some thermal energy, internal energy. So the way I'm going to picture that is Ki plus UGI plus W is equal to K final plus UG final plus delta U internal. Okay, so there's no external work done on this system, is what we're going to say. Because I've defined the system to be the box plus the Earth. So the mgh is the gravity work is taken up with this potential energy, and then also any work done by friction is taken up by this delta U internal. So what you do is you just write kinetic energy it's released from rest. I should also say assume. I'll write that better. Assume box begins and ends at rest. Okay, so you've got some initial gravitational, which I can make 4 boxes or something, plus 0 work is going to be 0 kinetic, plus it'll have a little less probably. I'm going to put 3 boxes because what will happen is one of these boxes will go out into that thermal energy. So you've got 0 plus mgh initial plus 0 equals 0 plus mgh final plus your F sub k times d. And then the other thing is that on a flat surface, you've got, if the normal force is up and F sub k is backwards and mg is down, then the sum of all the forces in the y direction is equal to 0 because it's not accelerating up or down. That's going to be 0 equals the normal force minus mg. So basically, the normal force equals mg. So what that means is that F sub k is equal to mu sub k times n. That's the equation for kinetic friction. You can just call it mu sub k times m times g. So this equation here becomes mg, if you take away all the zeros, mghi equals, too quickly here, equals mgh final plus mu sub k times mg times d. And what's interesting there is that the mg's cancel in all these equations, m times g, m times g, m times g. I can divide both sides by m times g. So that you've just got h initial equals h final plus mu sub k times d. So h final is equal to h initial minus mu sub k times d. So it's just equal to 2 minus 0.25 times 1.0. H final equals 1.75 meters. That's to 3 sig figs. And so it's not quite as high as initial. Okay, because some energy was lost to heat. That thing's gone blue. Okay, how are we doing here? Things get a little nasty if I leave this on, so I'm turning this off. Okay. Sometimes I get confused when to use the increase in the system's internal energy due to friction. Which cases do we use it? Anytime you have an object. So whenever there is some kinetic friction, then we've got this fact that during the process, if two surfaces slide against one another, you're generating some heat. And there's an equation for this, which is just that F sub k times d, where d is the distance. Okay. I think it's 0.25, Kathleen, is the, if we go back here, make sure I've got this right. 0.25 is the kinetic friction. Not 0.2. Okay. And then a 10.
Hello, Prof. Harlow.
Yes, hi.
I was wondering, so just to go back to the idea, to the the midterm assessment 4 and also the midterm assessment pre-quiz. I currently don't have access to a printer and therefore cannot print out the template. So is there any way I could write out my own and like just indicate all of the different steps?
Absolutely. Yeah, that's totally allowed. Just a template or a reasonable facsimile. So you can just write it on a piece of paper, and that's totally fine with me. As long as we can read it in the end. Arpit?
Hi, Professor.
Hey, how's it going?
I just wanted to talk to you about one more thing.
Sure.
It's just that the midterms are generally falling at a very odd timings, and even the alternate sitting is at an odd timing for me. Because
You know what?
the
I totally want to talk to you about this, Arpit, but I think that some people have figured out their time zones already. And, you know, we're warned about the timing of these Tuesday midterms back in September when you chose to take the course. And so they've rearranged their schedule so that every Tuesday on Toronto time at 8:10 and then 10:10 p.m., they're ready to do these midterms, okay? If 8:10 is a conflict, they go to the 10:10, otherwise you do the 8:10. It's gonna be, all 5 are gonna be the exact same time. I asked you to set aside time in your schedule back in September. It would have been, you know, a time to contact me about this. But now I just, you know, we can talk about it later, but not in the middle of class. All right. So moving along and moving forward, here is an energy diagram. So energy diagrams are very useful. And what you do is you make a plot of the potential energy versus position. Because potential energy, like MGH, for example, is an energy of position. If I have a tennis ball and I change it so that its Y position is up, it has a different potential energy. If I move it down again, different potential energy. If it's connected to a spring, same kind of thing. There's an energy of position. If I take the object and move it over here, it has more potential energy. If I move it over here, it has more potential energy, and its minimum is right here. So that's what we're showing in this parabola, is that potential energy has this shape. The curve is a parabola determined by the spring constant. And there it is, U sub s equals 1/2 k times x minus xe squared. So xe equals equilibrium position. It's the position where there's no force on the ball. No force on M at that position. That's why we call it equilibrium. The US curve is determined by the spring constant. You can't change it. What you can change is the total energy of the system. So you can start it by compressing it and releasing it from rest, or you could start it with some kinetic energy. And what happens here is that the kinetic K, so I guess the total energy E total, I guess from there, since E total, so kinetic is equal to, since E total is kinetic plus U sub S, then the kinetic is equal to E total minus U sub S. So it's this difference right here. So what this means, this is called K, is that K must be positive. K is always positive. If K is negative, it means it's not allowed. Or 0, right? You can't have a negative kinetic energy. So if you were over here, outside over to the left of this point or to the right of this point, the only way to be able to go over there would be to have negative kinetic energy, and you can't have that, so those are the turning points. This is where kinetic energy goes to 0, right there, K equals 0 and K equals 0. We call those turning points because that's where the speed goes to 0 and then it turns around. So what happens in reality is that it goes back and forth. It's called simple harmonic motion. We'll talk more about that later. Here is a more general energy diagram, okay? The particle might be released from rest here. Again, this is where K initial equals 0. And what could happen is that, so that's now the total energy, is that the particle will go towards the right. It'll speed up, then slow down, and then speed up again. There'll be a maximum speed when it gets to the lowest point, and then it'll go back up to K equals 0 at the very end there, and that's where it'll turn around. the particle reaches its maximum speed. When the particle reaches x5, it turns around and reverses the motion. So we can get all of this information about the motion of the particle just from looking at these energy diagrams. So I really like them. They come up in chemistry a lot. So this is a potential energy curve for an H2 molecule. You've got two hydrogen atoms that are bound by this covalent bond. And so if you look at the atomic separation of the two nuclei, the two protons, then what happens is that there is an energy. If they go too close, then these electrons repel one another, and there's a big energy associated with that. If they go farther away, then the energy goes up again. They want to come to an equilibrium position, which is right about here. Okay, and in nanometers, it's a little less than 0.1 nanometers, but it's called an angstrom of distance. So this is actually what determines the separation of the two protons in an H2 molecule. Is where is the potential energy curve a minimum? That's where the thing settles. And it can actually oscillate about that if you heat it up. And so this is a way of storing energy, internal energy in an H2 molecule, is having some vibrational modes here. But everything gets analyzed by looking at this potential energy curve. Okay, so what I want to do is it's team up time. Okay, so today, there's 3 multiple choice questions. You have to go on Quarkus to see them, but don't do them alone, please. I'd like you to do them as a team in your practicals pod. So please open up your Microsoft Teams. One of you, hopefully you're the facilitator last time or somebody that's chosen, should place a video call to the 3 or 4 members of your pod chat. I'm going to put myself on mute here pretty soon. The first step is to decide who will be the driver today. You all have to log on to Quarkus. Non-drivers, wait. The driver, go on to Team Up Quiz Chapter 7 in the Module 4. Click on Go to Tool, create a group, and then go back to your, to your chat and let everyone know the session ID. And then wait. Don't drive off alone. Wait for the non-drivers to get that session ID. Click Join Session and type it in, and then you'll all be together. Once everyone in your chat arrives in Team Up, start going through the questions. Please achieve consensus before the driver submits. So I'm going to put this thing on mute for 10 minutes. Right now it is 11:37. So we'll stop this at 11:47. Okay, everybody's 1 minute. And we're gonna come back. Cayman, you've had your hand up a couple times. How's it going?
Yeah. Hello, Mr. Harlow. Can
Yes,
you hear
hi.
me?
Yes, I can. Yeah,
Yeah. Do you remember me?
yeah, kind of. Yeah.
Yeah, I'm famous, right?
Yeah.
Okay. I have a question. For me, for the midterm assessments,
Yeah.
like writing like solutions down 2 questions
Yeah.
for 30 minutes was much suitable for me. Like what do you say? Like multiple choice questions. Like I've never like did multiple choice question format in past physics courses.
Yeah.
So like, yeah. So will the midterm assessment 5 and final exam be written response again?
Yeah, that's a good question. So yeah, midterm assessment 5 will be fully multiple choice, again, 10 multiple choice questions. And then the final exam will have elements of both. It's going to be basically like 2 of these quizzes. One will be multiple choice, and then one will be written out. So I want to go over these team up questions. Hopefully it went well and you were able to have a chat about these things with your pod members. Certainly, the idea here is that H initial is the same for all 3. And then here, H final is the same for all 3. Okay, so you define the system equals ball plus earth, and you're going to get that the final kinetic energy is going to be the same for all of them. They start with the same initial kinetic energy. You just got K initial plus UG initial equals K final plus UG final. That's all it is. This one was a little harder. So then this has to do, the way I solved this was using this idea of kinetic energy. So K final cannot be negative. If it is negative, that's bad. Okay, it means that you can't get there. Okay, you could, I don't know, this, you'd have a complex speed or something like that. So what you do is you do the system is puck plus earth. And so you've got K initial plus UG initial equals K final plus UG final. There's no work done on that system. So 1/2 mv initial squared plus 0 is equal to the K final plus mg times H final. And so what we can do is we can divide both sides by m, which it's mass, so that's positive for sure. And then we can also isolate K sub f, which is what's important. And what I got there is K sub f divided by m is equal to 1/2 vi squared minus g times h. So you can actually calculate that. It's 1/2 of 4 squared minus 9.8 times 1.0. So if you actually work that out, 4 squared is 16, half of that is 8 minus 9.8 is negative 1.8 joules per kilogram or something like that. So this is not possible. Kinetic energy must be positive. Mass must be positive as well. So if you get a negative number here, what it means in real life is that it's going to go up, it's going to turn around less than 1 meter, and it's going to come back down again. It doesn't make it to the top of the hill. That was a tricky one. Hopefully you guys got it. Two objects collide, all external forces on the object are negligible. So this is a vocab question. If it's totally inelastic, you can find that in your book you're reading for today. It means that the objects stick together. Josephine, question?
Hi, two quick questions. So for this question,
Yeah.
I mean, second one,
Yeah, second.
sorry, the one before.
Yep.
Instead of doing the solving for the kinetic energy final, I did like Ki equals UGF, and I solved for how high it would go, assuming it would come to rest.
That's a good idea. And then you got less than 1 meter, right?
Yes, I got 0.8. So is that
Yeah.
still a valid way of solving this?
Yeah, that's fine. That's a good way. I like that way.
And then
So
the
then,
second,
yeah,
oh yes. I know this is a little far ahead, but for the final assessment, is it cumulative of all we've done this semester, or is it just the last 2 or so units?
yeah, it's the entire semester. So the final assessment, which I think is going to be on December 17th, it'll be based on the entire course from September all the way through. But that last midterm assessment 5 will just be on the previous 2 chapters.
Oh, okay, thanks.
Okay, sure. Excellent questions. I like it when people ask questions that everyone's thinking, right? You are all thinking these questions, and it's good to ask them so that I actually address it. Ethan, did you have a question?
Hello.
Hi.
So for the first question,
Yeah. Can team up?
when you're throwing the ball in different like direction, like downward, horizontal, or at an angle, wouldn't you say there's like work applied to it? So the energy is different.
Yeah. So the idea is here that energy is a scalar. It has no direction associated with it. So now certainly the trajectories and the timing of all these things are going to be different. If you send it up, then the force is going to be, slowing it down at first and then speeding it up. If you send it down, it's just going to speed up. So the work will do different things. But if all you're comparing is just initial, which is a certain height and certain initial energy, to final, which is at a certain height and a certain kinetic energy, then it doesn't matter what happened in between, is what I'm saying. And no matter what direction I send those objects in, if they are the same speed, the direction doesn't affect the kinetic energy.
Okay. Yeah. Thank you.
Okay. Yeah. Again, great question. Okay. So what are we doing next? Oh, we had a demonstration I wanted to do. So this is about elastic collisions. See if I have time to do it. A perfectly elastic collision conserves both momentum and this mechanical energy, so the sum of the kinetic plus the potential. So here's an elastic collision in one dimension when ball 2 is initially at rest. So we consider as a head-on perfectly elastic collision of a ball of mass m1 having initial velocity v1I with a ball of mass m2 that's initially at rest. During the collision, energy gets stored as elastic potential energy because the balls squish. But then afterwards, if it's elastic, then the kinetic energy final is equal to the kinetic energy initial. The ball's velocities after the collision are v1f and v2f. So you can have a momentum conservation equation and a kinetic energy conservation equation, and these are 2 equations and 2 unknowns, v1f and v2f, and you can solve those out. And this was done in the textbook in an example. But these are equations that are handy to have, and they're going to stay here on this slide. So what I wanted to do with this example was I have a 0.5 kilogram basketball, and I have a tennis ball. I'm going to drop them from some height and stack them up, drop them, and see what happens. How high does the tennis ball bounce? And we're going to assume all are perfectly elastic collisions. So I can actually try to do a demo of that before we do it. Whoops. Okay, everybody, hopefully you can see me. What I'm going to do is drop these two things from about a height of here. Try to balance them up. Whoa! That didn't work too well. I think my hands are a little shaky there. So let's try it again. See if I can get it to go straight up. 1, 2, 3. Whoa! Okay. So it goes way high up. Okay, so that's your demo. Share screen again. Make sure I have my chat window. Okay. So segment 1, both of them are freely falling and they're released from rest. Segment 2 is that the basketball collides with the floor elastically, and the tennis ball, if there's a little gap, will continue down unaffected. Segment 3 is that there's an elastic collision of the upward moving basketball with the downward moving tennis ball. And segment 4 is free fall of the upward moving tennis ball. And you're going to try to find what the final height is of that tennis ball. So I've divided the motion into segments. Segment 1, it's just if they have a height initial is equal to 0.82 meters, then you can use conservation of energy. You end up with -4 meters per second for both balls. Segment 2 is that the basketball collides elastically with the floor and it's going at then +4 meters per second. And then segment 3 is what you've got is a basketball moving upwards at 4.0 meters per second and a tennis ball moving downwards at 4 meters per second. So their collision is perfectly elastic. What is the speed of the tennis ball immediately after the collision? So I'm going to phrase this as being an example. You have a 0.5 kilogram basketball moving upwards at 4.0 meters per second squared, and it collides elastically with a tennis ball moving downward at 4 meters per second. Get this right. Basketball moving upward at 4.0 meters per second strikes a 0.5 kilogram tennis ball, initially moving downwards at 4 meters per second. Their collision is perfectly elastic. What is the speed of the tennis ball immediately after the collision? So these equations work for the ball 2 being initially at rest. So you can't use them in this case unless you go to the reference frame of the tennis ball in which the tennis ball is at rest. So I'm going to do this on Monday, since I don't really have time to do that right now. The answer is going to be plus 10.5 meters per second. Once we go to back to the lab frame. So, and then that you see that the tennis ball goes up to 5.6 meters, which is why it hit the roof. So that's it for today. I will go through and carefully do that elastic collision calculation on Monday morning. Over the weekend, please have a read over chapter 7.8, section on power, and then section 7.9 on gravitational potential energy out in space. Remember, on Tuesday, November 3rd, by 8:45 p.m., you have to upload your chapter 7 pre-quiz onto that CrowdMark site. I'll be going through that afterwards, and it's worth 16 homework credits for good faith participation by the deadline. This one will not be carefully marked. So thank you very much, and everybody have a fantastic weekend.